Now let's look at some examples of algorithms implemented in parallel using MapReduce. For those of you used to relational databases, here's how one can implement a join using MapReduce. Suppose we're given two tables, sales by address and cities by address, and we are interested in joining these tables to find the sales by city. In SQL, this is how you do it. You'd simply select the sum of sales from these two tables where the addresses match and group them by city. However, in MapReduce, this requires two MapReduce jobs. In the first case, you join, or essentially sort, the data by address so that each reducer is able to emit the city for every sale. So in other words, the first MapReduce task only joins the sales and cities table but doesn't do the grouping. In the second MapReduce task, we sort on the city key so that all the records for a particular city come to the same reducer where the addition takes place. Notice that we couldn't have used a single MapReduce phase because at the end of the first phase, it's not possible to guarantee that all the data for a particular city resides in the same reducer, and so the summation can't be done, at least city-wise, in a single phase. I'll relate to you a real-world story that illustrates the difference between the MapReduce way of thinking and a traditional database approach. This is a real example where an organization had lots of data which could be abstracted as data about papers, their authors, and their contents. The actual nature of the data is proprietary, so I won't relate that in detail. But it's pretty much the same problem as this. There are millions of papers written by many millions of authors containing millions of possible technical terms, phrases, multi-word terms. And one of the tasks was to figure out the top 10 technical terms used by each author, the top 10 authors that used a particular term, and so on. As you can see, this problem is quite close to our word counting example and possibly indicates a real-life requirement as well. This is how a database person actually proposed a solution. You start out with a bunch of documents represented as a table with, say, a paper ID, the content of the document itself, and its author. Then you get rid of the actual content and replace it by words. Notice what has happened over here. Instead of one row per paper, now you only have a row for a word and author pair that occurs in a particular paper. So one row here will produce many, many rows in the table queue. No matter, says our database expert. All we need to do is now do a group by so that we can count how many times a particular word is used by a particular author. So the resulting table would let you answer questions about which are the top 10 technical terms used by a particular author by simply finding all the entries for an author, sorting them by word count, and you have your answer. Problems start to occur when you try to consider how large these tables can get. If this P has a million or a few million documents, then let's take a look at this table here. At worst, you'll have an entry for every word and every author, that is if you allow 0 word counts. That works out to million into million or a trillion entries. Even if you don't have zeros and you get rid of them by suitable modifications to your joining and counting process, you'll still have many billions of entries in this table merely to solve this kind of a problem. Now suppose you wanted to find the top 10 authors for two terms, say a combination of terms, or you wanted to find the top 10 terms for two authors who wrote together. This solution doesn't work anymore. So we see that the database mindset doesn't quite work in such high dimensional spaces where you have millions of terms and millions of authors and you're trying to find counts of combinations between them. This is really a case for MapReduce, and it is exactly these types of challenges which led the web companies to develop new technologies and new programming paradigms. It was not just that the old technologies didn't scale, it's the fact that the relational paradigm itself needed to be looked at afresh when dealing with large volumes of unstructured data. Okay, so let's try doing top K words per author in MapReduce. Well, suppose we use the map function where you emit a word and author every time you see it in a document, just like we emitted the word and its counts earlier. And the reduce key is a word-author combination so that every reducer gets all the records which have one such combination and can simply count them. Well, this doesn't quite solve the problem, or does it? Actually, it's the same problem as before, a database mindset being used with MapReduce. So it's the programming paradigm is not a solution by itself. The approach really needs to change from a database-oriented one to something else. Let's try it again. Again, we have a map function, but this time, instead of emitting the author and the word, we emit the author and the content. So essentially, all the map phase is doing is extracting the author field and emitting it along with the contents. In the reduce phase, we group everything by author so that all the documents for a particular author end up being in the same reducer. And then the reduce function is a custom function which works as follows. For each author, this reduce function grabs all the elements in that reducer for that author, computes the word counts, inserts into some temporary array W, sorts it, figures out the top K words for that author, deletes the W, and starts again for the next author. Essentially, you're computing the top K for each author, not storing the combination of each word author, because you're only interested in the top K, the top 10, the top 5, the top 20, whatever. Notice what we've done here. We're bringing some element of programming back into the reduce function and not relying entirely on the system, MapReduce in this case, or the database in the previous case, to do all our work. Now let's look at some more examples such as those we have considered in the past few weeks. Indexing, locality-sensitive hashing, in particular how to assemble the results from many different hash functions, how to compute the likelihoods while coming up with a Bayesian classifier, and how to evaluate a Bayesian classifier to compute the likelihood ratio. Do you actually need parallelism to do this? How about computing the TF-IDF or the joint probabilities for computing the information gain or mutual information. I'll leave these last three as homework for you, and we'll just do the first three right now. Let's start with indexing. In the map phase, we produce a partial index for a partial set of documents. That is, we emit for every word the postings list out of all the documents that we see. This is not a full index, so we have to reduce again by word and merge the partial indexes, that is, merge these postings lists per word into a common postings list. An interesting question is, what if you had to sort either by document ID or by page rank as we had in our first homework assignment? What do you think you'd need to do then? Would you need another MapReduce phase? Think about it. Now let's consider locality sensitive hashing. The map phase, you start with documents and compute k hash values for every document. These could be the k hash values we used for fingerprints, or they could be others as are described in the Rajaram book for documents. The reduce key is now the k hash functions. Each reducer gets all those documents that have the same k hash values and figures out all the pairs that they could possibly form. So if there are 3 documents, it emits 3 pairs. If there are 4 documents, it emits 6 pairs, and so on. As a result, the MapReduce LSH produces a list of document pairs which are potentially similar. An interesting question is, will a document pair be emitted by more than one reducer? And suppose we wanted each pair to be emitted only once. What would we do then? Lastly, let's come to our Bayesian classifier, where we need to compute the likelihoods, or rather the conditional probabilities, of a yes occurring or a no occurring for each possible feature. So the map phase merely produces the counts of feature yes or feature no, which are then grouped by features in the reduce phase so that we get all the counts that were emitted for a particular feature in one reducer, where we merely sum up the respective counts and divide by the total number of instances that we've seen for a particular feature. Finally, we emit the log of this likelihood so that we get the elements of our Bayesian classifier. Notice that once we have the log likelihoods for each feature, do we really need parallelism for testing new documents or new objects using the naive Bayes classifier? Think about it. Is that computation really that large as to require parallel computing? Well, we've seen a number of examples of MapReduce. Admittedly, the last few have been covered rather quickly. Please review the material so that you understand it, and discuss it if you don't in the forum.